Good afternoon, everyone. My name is Kevin Farrugia, and I'm presenting the paper named Demystifying the Voynich Manuscript using computational linguistic techniques. I would like to start this presentation with a brief introduction to myself. I have recently graduated from the University of Malta with a bachelor's degree in human language technology, and I'm currently reading for a master's degree in data science. In my free time, I love reading on history and occasionally play video games that let you experience a different era. One of the video games that I found myself indulging in lets the player explore the 18th century Caribbean and find various treasures, some of which were folios from the mysterious Voynich Manuscript. As you can see, it let you find 4 different folios, which I managed to find all of them, and for each there's a brief description. So the game developers put some effort into doing a little bit of research on the manuscript. The manuscript immediately caught my interest. It is a historical object with many unanswered questions, such as what does the text mean, if it has any meaning, why was it written, who were its authors, and how many were there, as well as who were its writers and how many were there. This last question is the focus of the paper I'm presenting today. Together with my co-writers, Dr. Colin Layfield and Professor Voynich van der Plas, we approach this question with a computational linguistic lens. We're not the first to have asked this question, and the existing work on this topic serves as the basis for this paper. Albert Howard Carter, Erwin Panofsky, Captain Prescott Carrier, and Mary D'Imperio have all commented on or researched the possible number of hands responsible for the manuscript's text, as well as theorized on which folios were written by which hand. Carrier used 2 methods to do so. The first was analyzing visual variation in handwriting, and the differences he noticed here were named different hands. And the second method was by analyzing frequency variation in character level patterns. And the differences he noticed in this case he labeled as different languages. And this distinction between the hands and the languages is very relevant as well. However, the most relevant work for us is the paper named How Many Glyphs and How Many Scribes, Digital Palaeography and the Voynich Manuscript. Dr. Lisa Fagan-Davis, its author, which I believe is present for this conference, makes use of digital palaeography tools, as well as her own expertise, to identify 5 scribes in the manuscript. Each page is labeled as being the work of one of these 5 scribes. This labeling of pages to scribes is used as the basis for our experiment. Here we can see an example, a sample from Dr. Davis's classification. On the left side, you can specifically the folios column and the scribe column. We can see how each folio is usually attributed to a single scribe. There are cases where different parts of the folios seem to have been written by different scribes, but the vast majority is a one-to-one relationship between a folio and a scribe. And this serves as the label data set for our experiments. So our research question is the following. Does the classification of folios into scribes, as we have just seen, and as proposed in palaeographic works, hold out when cross-validated by means of automatic authorship attribution methods? I will explain what I mean by these methods in the next slide. Whilst answering this question, we'll also be investigating what components of the undeciphered text of the Voynich manuscript are adequate to use as features that determine one scribe from the other. Also, which pages of the manuscript prove to be more difficult than others to categorize into scribes as proposed by the findings in Davis' work. Before I proceed any further, I would like to make a clarification. An author is clearly different from a scribe, as one could be dictating whilst the other writing. In this paper, we assume that the scribes of the Voynich manuscript were independent from any authors. I will elaborate on this when discussing the results. So what about authorship attribution? The Voynich Manuscript is not the only example of an authorship attribution problem. There are years of research and well-studied methods which solve different forms of this problem. An example of such a problem is as follows. Let's say a mystery book has been discovered, but there is no hint of who the author is. Researchers have boiled it down to being either Shakespeare, Marlowe, or Kidd. However, which one it is, they cannot find out. So how do we solve this problem? We first need to learn what distinguishes each author from the others. After we learn this, we can then look at the mystery book and find these distinguishing features. Does it have the same features as one of the proposed authors with a good degree of confidence? Simply being more similar to one of the authors is simply not enough. It has to be similar enough and similar only to that particular author so that you can attribute that author to that book. Therefore, authorship attribution has two requirements. You first need data. For example, if we go back to our previous example, we need Shakespeare's plays and Shakespeare's books, so that from them we can extract those features, which is the second requirement for authorship attribution, that define this author from others. So we need the data and the features. What is the problem with the Voynich manuscript is that there are a number of issues in this regard. Firstly, there is only one known document written in Voynich script, and I do not believe there are other documents that have been identified as being the works as the same person or persons as the Voynich manuscript. Therefore, a classifier has no outside information to learn from. The second problem is that the language has not yet been deciphered. This makes it difficult for the classifier to choose the linguistic features, such as morphological, syntactic, or semantic, which best differentiate between different scribes. To resolve these issues, we change the problem statement. Instead of attributing an author for the entirety of the manuscript, we attribute scribes for the individual pages of the manuscript, so we drill down to a page-level analysis. The result of Dr. Davis's palaeographic analysis serve as the label data, like Shakespeare's books and plays in the previous example, and as features to identify between the scribes. Stylistic features are ideal, as they are independent from the unknown meanings of the words in the Voynich manuscript. Therefore, character engrams are used, specifically bigrams and trigrams. So what are character engrams? These are groupings of 2 or 3 consecutive characters, because we're looking at bigrams and trigrams. All the distinct groupings in a page are identified and counted, from which scribe identification patterns are obtained. This means that the distribution of engram counts of a scribe is distinctively different than the distribution of engram counts of another scribe. A problem with using character engrams is that they may indicate topicality rather than authorship. The way that we deal with this problem is to select high-frequency character engrams only, and we leave out the low-frequency ones from our data. In our case, we chose a cutoff point of 50, so anything with a frequency higher than 50 is selected, and anything less is removed. Having both our labeled data and features, we could start the experiment. This was designed to reflect the main research question. So, if we are to build a machine learning classification model on a part of Dr. Davis's labeled pages, then use the model to predict another part, will the model attribute the same scribes to the same folios as Dr. Davis? This is integrated in a cross-validation process where on every iteration a new part of the labeled dataset is excluded in the training of the model, as we can see in the table. So we start with the entire dataset, which is split into equal parts and to 10 equal parts. Then we take 9 of those parts, we build a model which we use to predict the other 10%. This is the flowchart of the methodology that was used in the experiment. So we're starting with a transliteration of the Voynich manuscript, It is in the extensible Voynich alphabet by Renes and Bergen, in the intermediate Voynich transliteration file format. This is handy because it comes with a tool which we use to remove some unnecessary data, such as the annotations in the manuscript. After doing so, we add the labels to the folios, to the pages of this data. So we add Dr. Davis's classification to the data. Following this tabling, we stratified data, that is, we balance the amount of data between the scribes. And this will be explained in the next slide in more detail. And after doing so, we can start our classification and cross-validation. The first step is to split the data set that we have into a set that is 90% of the data set, which will be the training set, and the testing set which will be the remaining 10%. And we featureize the data as character engrams. And we do this on every iteration of the cross-validation so that we avoid information leakage. After featureizing, we pass on this information to the classification machine learning classifiers. We are using 4 different ones: the deep neural network, multinomial naive Bayes, support vector machines, and a decision tree classifier. And they make their predictions on the test set, and we get these predictions so that we compare them with the ground truth. By ground truth, I mean the classification made by Dr. Davis. So what did I mean when I mentioned the class balancing, the stratification? So the left table here, it shows us the original counts of the Voynich manuscript. So how many pages did each scribe write? And as we can see there, we have a variety of numbers there. So scribe 1 had 107, which was the highest count, while scribe 5 had only 7. We decided to not use scribes 4 and 5 because of the relatively low number of pages. So we focused on the first 3 scribes, and the one which has the lowest is scribe 331. So we balanced the other 2 scribes to match this number, as we can see on the right-hand side table. Something that interesting that came out from this was that as we can see, they all have the same number of pages, but the number of words and characters is very different. And this shows that scribe 3, in this case, was responsible for pages that had a lot of text in them, while scribes 1 pages probably had not so much text and maybe more images. You can see an example of this here. So on the left we have a folio 33V, which was written by scribe 2, and on the right we have folio 104V, which was written by scribe 3, and the density in the text is very different, as the one on the left has an image taking up most of the space. So these are the confusion matrices for the 4 different classifiers for the 2 different experiments. And we have the character trigrams experiment on the left and the one using character bigrams on the right. The way that you interpret these is, so a confusion matrix shows us, so when a classifier predicts the same scribe as our ground truth, and it also shows us when a classifier attributes a scribe to a page differently from the ground truth. So the way that you will read this is this diagonal, starting from the top left corner going down to the top right corner, would be all those instances where the classifier has agreed with the ground truth, and the rest would be accounts of the instances where it did not agree. For example, for scribe 1, the deep neural network using character trigrams, 30 of the 31 pages were attributed to scribe 1 and agreed with the ground truth. Only 1 page should have been, well, not should have been, but was attributed to scribe 3 by the classifier, but was attributed as scribe 1 by Dr. Davis. And so that is how you interpret these confusion matrices. An interesting thing that we can see by looking at the entire the entirety of this slide is that in the heat map, we can see that the coloration at the bottom right corners of each confusion matrix is slightly darker for when the classifier disagrees with the ground truth. For example, the clearest representation of this is the decision declassifier on this side, where it is confusing between scribes 2 and scribes 3, but not so much between scribe 1 and the other two scribes. And we can see this for practically all of the confusion matrices. What conclusion can we draw from this? It could possibly mean that the confusion between scribes 2 and 3, it could indicate that they were of the same author but different scribes. So they still have stylometric differences, however, it's not as much as the differences between scribes 2 and 3 collectively and scribe 1. We can summarize those results in one table. So here we can see how many times did a classifier agree with the ground truth as a percentage. When we combine these together, those instances where all 4 classifiers attributed the same scribe to a page sum up to 68.8% when using trigrams. So in nearly 70% of the data, we have an agreement between all of the classifiers and the ground truth. This goes down to about 50% when we use character bigrams in our experiments. So what about the disagreement with the ground truth? When do the classifiers not agree with the ground truth? Well, there's different cases. So you could have only one classifier which does not agree. You could have 2 which do not agree. You could have 3 or all 4. I think the most important thing to look at is when all 4 classifiers are in disagreement with the ground truth, but they are in agreement with one another. So they all say that it is a particular scribe, and this is not in agreement with the ground truth. And I have isolated these examples from both experiments to be these particular pages. So, for example, using the trigrams, we have folio 39 verso, which was labeled as scribe 2, but all 4 classifiers disagree with this, and they say that this should have been labeled as scribe 3. And the same goes for the other table in the bigrams experiment. For example, we have folio 57V, which was labeled as scribe 1 by Dr. Davis, but all the classifiers agreed that this was scribe 3. What we conclude from these findings. So confusion occurs mostly between scribes 2 and 3. Scribe 1 is rarely confused with the others. And this may, as I have mentioned earlier, indicate that scribes 2 and 3 had the same author, possibly, while scribe 1 was entirely separate. Using character bigrams resulted in around 50% of the pages being classified by all classifiers in the same way as the ground truth, while this goes up to 70% when using trigrams. Around 14% of all pages were classified to be different from the ground truth by the majority, so that's at least 3 of the classifiers in the experiment when using bigrams, and this goes up to 10.8% when using trigrams. And this value increases to 22.6% and 14% respectively when considering at least 2 disagreeing classifiers. So for the most part, the classification of the machine learning classifiers was actually in agreement with what Dr. Davis said. And those very few instances where there's agreement between classifiers and they all disagree with the ground truth have been laid out here for future work to look into them further and see why this came out from this experiment. That's all. I would like to thank you for for your attention, and I hope it was interesting for everyone to hear. And goodbye and enjoy the rest of the conference.